Hi, my name is Madi and this is my Physics 2211 Lab 2, Motion of a Falling Object. In this lab, I measure an object's motion from being dropped at rest. I will also compare the observed motion from the object to two computational models to see how the two different known forces of gravity and drag force can affect position and how well they predict the motion observed. Results show that the more forces that are taken into consideration, aka the drag force, the more accurate the predictive value of the computational model becomes. My computational model that considered both drag force and force of gravitation was more accurate than my computational model that did not consider drag force. The first key concept in this lab is Newton's second law, which says the net force acting on an object is the change in momentum divided by the change in time. When we're looking at the motion of an object, we can manipulate this formula to get the velocity update formula and the position update formula. The velocity update formula relates the velocity of an object to the force acting on the object, and the position update formula relates position and average velocity. Another key concept in this lab is gravitational force. The gravitational force acting on an object near Earth's surface is the product of the object's mass and acceleration due to gravity in the negative y direction. We can equate this formula to the universal law of gravitation, which is the second formula in this slide. We can also manipulate the universal law of gravitation to help us find the actual value of g on Earth, which is 9.8 meters per second squared. The final key concept in this lab is the drag force acting on the object. Drag force acts in the opposite direction of the object's motion, opposing this force. The drag force is in the positive y direction in this lab because our object is falling. The formula uses the drag coefficient in the square of the magnitude of velocity of the object. Here I have also included some free body diagrams to demonstrate the forces acting on the object over a particular time interval. As time increases, so does drag force. This happens because the magnitude of velocity increases over time for the opposite, which is directly proportional to the drag force. In this example, our system is the ball and our surroundings are everything else. This is a photo of how I used tracker analysis to measure the ball's motion. The origin of the axis is at time equals 0 seconds, and we can see from the track graph that the ball moves in the negative y direction. We can see that the initial position of our object is 0.0032 meters in the x component and 0 meters in the y and z components. The amount of time it took my object to reach the ground was 0.458 seconds. My initial velocity is 0 meters per second in all components since the object is being dropped from rest. The object's speed increases with time and there is no constant motion on the object. This indicates that there are other forces acting besides gravity on my object. This is a snippet of my code for the computational model with no drag force. We can see there is no drag force because our proportionality constant is equal to 0 in my code. The initial conditions are my initial conditions I got from the track graph. In my iterative loop, I included Newton's second law in the form of the velocity update formula and the position update formula, as we can see in my GlowScript code. The iterations are around 1/55th of a second, and the while loop runs until it reaches 0.458 seconds. These are my initial conditions for the computational model that does consider drag force. We can see a key difference here that my proportionality constant has a value of a non-zero positive number, which is 0.0865. This is the iteration step for my computational model considering drag force also. This code is different than my other computational model because we can see that I am now factoring in both drag force and gravitational force into my net force calculation. Here are snippets of my code used to draw arrows that represent the force of gravity and the drag force on the ball. The graphical results of my experiment are shown on this slide as a position versus time graph, where position is measured in meters from the origin as time is measured in seconds. The data points in blue are for my experimental model, the data points in red are for the computational model without drag, and the data points in yellow are for the computational model with drag considered. We have an overestimation in the change of position by the computational model that does not consider drag force, which suggests that there's another force opposing gravity in this experiment. The computational model that does consider drag force is much more accurate than the one that does not consider drag force because there's definitely another force besides gravity acting on this Raja model. We can assume some forces of error may be not accounting for motion in other directions, measuring the center of the ball incorrectly, incorrect drag coefficient measuring, or rounding errors in our code. Out of the two computational models, the model that does include the drag force predicts a terminal velocity. We can see that in the velocity versus time graphs that the model including drag force predicts a decrease in the magnitude of change in velocity, and we can see a horizontal asymptote starting to form at the bottom of the graph. To test this what-if question, we should change the initial velocity for the model considering drag force and make it a non-zero in the negative y direction. This shows that the terminal velocity that approaches an asymptote is reached sooner than when the ball is at rest. However, since the terminal velocity is still quite similar, this suggests it does not change even when the initial velocity is a non-zero number. Thank you.